You know that feeling, right? Staring at, like, a mountain of study notes.
Oh, yeah. Brain fade deluxe.
Exactly. And you just wish someone would lay it all out clearly. So that's what we're tackling today.
We are diving deep.
Deep into something huge.
Yeah.
The origin and, well, the evolution of Earth and the universe.
It's pretty fundamental stuff. Connects to so much else.
Totally. Think of this as, your guide to the big picture. We're looking at the key ideas, the early theories, right up to our modern understanding.
Absolutely. It's a story billions of years in the making. And honestly, when you see how it fits together, it's kind of amazing. We'll unpack the ideas, the evidence, the stuff that helps it all click.
Perfect. So let's jump right in. That big question, how did any of this begin? Earth, stars, space. Where did it all come from? Maybe start with the earliest scientific ideas about Earth's formation.
Okay. Well, the first sort of scientific attempts really got going back in the 18th century.
Right.
There was Immanuel Kant, the philosopher. He suggested planets formed from, like, a cloud of material, dust and gas.
Wow.
Then later, a mathematician, Laplace, he refined that idea around 1796. That became known as the nebular hypothesis.
The nebular hypothesis. Okay, so that was a big early one. What was the actual idea? Like, what did it look like?
The core concept was our solar system starting as this huge, slowly spinning cloud, gas and dust, all connected somehow to a young sun.
Like a giant cosmic cloud swirling.
Yeah, exactly. Swirling and gradually flattening out into a disc shape.
Okay, like spinning pizza dough, but cosmic scale.
Yeah.
But I'm guessing things have moved on a bit since 1796.
Oh, absolutely. Fast forward to the mid-20th century, around 1950, you had Otto Schmidt in Russia and Carl Weizsäcker in Germany. They revisited that nebular hypothesis.
Right, updated it.
Yeah, they proposed the early sun was surrounded by something they called a solar nebula.
Solar nebula.
Yeah.
Okay, what was that made of? What's in the mix?
Mostly the basics. Hydrogen and helium. I mean, they're the most common things in the universe, right?
All right.
But crucially, there was also dust. Tiny particles of heavier stuff forged inside older stars that had, lived and died.
Okay, so hydrogen, helium, and this stardust. How did that cloud turn into, planets like ours?
So Schmidt and Weizsäcker figured that inside this flat, spinning cloud, all these tiny bits gas molecules, dust particles, were constantly bumping into each other, gently colliding.
Bumping into each other.
Yeah, and over long periods, these collisions weren't just bounces. They started sticking together. It's a process called accretion.
Accretion, like sticking.
Exactly. Think of, like, microscopic dust bunnies bumping and clumping. Over millions and millions of years, this builds up.
Wow.
It's kind of mind-blowing that the ground we're standing on started like that, tiny specks sticking together, and as these clumps got bigger...
Gravity starts to play a role.
You got it. Their own gravity pulled in more stuff faster. They grew into what we call planetesimals.
Planetesimals, so like mini planets. Lots of them.
Yeah, loads of these smaller bodies. Then they started colliding and merging, sticking together through gravity again, forming fewer but much bigger objects.
And those became the planets we see today.
That's the idea. Over vast timescales, yeah.
Incredible.
Yeah.
So the nebular hypothesis evolved from a general cloud idea to this solar nebula accretion planetesimals. But it feels like science then zoomed out, right, to the whole universe, not just us.
That's a really good point. As our tools got better, bigger telescopes, understanding physics more deeply, it became obvious you couldn't fully grasp our solar system without looking at the bigger picture.
The cosmic context.
Exactly. And that led to modern cosmology. And the main theory there, the cornerstone, is the Big Bang theory.
Ah, the Big Bang. Everyone's heard of that one. So break it down simply. What does it say about the very beginning?
Okay, the Big Bang theory, or the expanding universe hypothesis, basically says the universe started from this incredibly hot, incredibly dense state about 13.7 billion years ago.
13.7 billion.
Yeah.
Wow. What's the evidence for that?
The crucial evidence really came together in 1920. Edwin Hubble. Your notes probably mention him.
Hubble, yeah. The telescope guy.
Yeah.
Well, named after him.
That's the one. He made these amazing observations showing galaxies aren't just sitting there. They're actually moving away from us and from each other.
Moving away. How could he tell that just by looking?
It's about the light. He studied the light from distant galaxies and noticed something called redshift.
Redshift, meaning?
Meaning the light waves were stretched out, shifted towards the red end of the spectrum. And the really key thing, the farther away the galaxy, the bigger the redshift, the faster it seemed to be moving away.
Okay. Like the sound of an ambulance siren changing pitch.
Exactly like that. It's the Doppler effect, but for light. It tells us they're receding, and space itself is stretching, expanding.
Right, the expanding universe. I've heard the balloon analogy used for this. Can you explain that?
Sure, it's helpful up to a point. Imagine you have a balloon, maybe put some dots on it.
Okay, dots are galaxies.
Yep. Now, blow up the balloon, what happens to the dots?
They all move further apart from each other.
Exactly. So that visualizes how the space between the galaxies is expanding, pushing them apart.
That makes sense. But I remember reading, it's not a perfect analogy. What's the catch?
The main catch is, on the balloon, the dots themselves stretch out as it inflates.
Ah, but real galaxies don't stretch.
Right. Observations show galaxies are held together by their own gravity. They aren't expanding internally like the dots on the balloon. So the analogy shows the expansion between things, but it breaks down a bit on the scale of the objects themselves.
Got it. Space between galaxies stretches, galaxies themselves don't. Okay, back to the very, very beginning. This tiny ball they talk about. What was that?
Well, the theory suggests that right at the start, everything, all matter, all energy, it was concentrated into an unbelievably small volume. We call it a singularity.
A singularity, not like a tiny atom.
No, think smaller. Infinitesimally small volume, but with basically infinite temperature and infinite density, all the stuff of the universe crammed in.
Infinite temperature, infinite density. That's hard to get your head around.
Yeah.
So what happened next? The bang.
Around 13.7 billion years ago, yeah. This singularity underwent this massive rapid expansion, the Big Bang. But it wasn't like a bomb exploding in space.
Right, you said that earlier.
It was space itself expanding extremely rapidly, unbelievably fast in the first tiny fractions of a second. And as it expanded, it also cooled. Some of that immense energy converted into matter. You MC a call.
So matter. The stuff we're made of literally came from energy right at the start.
That's the picture, yeah. And incredibly, within just the first 3 minutes, things had cooled enough for the first atomic nuclei to form.
3 minutes.
Already. Yep. Protons and neutrons could stick together to make the nuclei of the simplest elements, mostly hydrogen and helium, the basic building blocks.
Okay, so a hot soup of basic nuclei. What happened over the next while?
Well, the universe kept expanding and cooling, but for about 300,000 years, it was still too hot for stable atoms to form. It was this hot, dense, plasma-charged particles whizzing around. Light couldn't travel far.
Like a thick fog.
Sort of, yeah. Then, around 300,000 years after the Big Bang, the temperature dropped enough, maybe 4,500 Kelvin, still super hot, but cool enough.
Cool enough for what?
For electrons to combine with those nuclei and form neutral atoms, hydrogen and helium atoms mainly. And that was crucial because it made the universe transparent.
Transparent.
Yeah, light could suddenly travel freely through space without constantly bumping into charged particles. That ancient light from that moment is something we can still detect today. It's called the cosmic microwave background radiation.
Ah, the CMB. That's big evidence for the Big Bang, right?
Absolutely. A major piece of evidence. It's like the afterglow of that early hot phase.
Okay, so expansion means space between galaxies grows, it cools, atoms form, universe becomes transparent. Now, you mentioned another theory briefly, Hoyle's steady state.
Ah, yes. Fred Hoyle and others, back in the mid-20th century, proposed an alternative, the steady state theory.
What was the idea there?
They suggested the universe didn't have a beginning like the Big Bang. They thought it always existed, looking roughly the same. As it expanded, new matter was continuously created out of nothing, basically, to keep the density constant.
Huh. A universe that always was, always expanding, but always at the same density? Why didn't that catch on? Why the Big Bang now?
Mostly, the evidence just stacked up against steady state and for the Big Bang. That cosmic microwave background discovery in the 60s was huge. Steady state couldn't really explain it.
The afterglow.
Exactly. Plus, things like the amount of hydrogen and helium we actually see in the universe matched the Big Bang predictions really well. Steady state struggled with those observations, so the evidence just pointed much more strongly towards the Big Bang model.
Makes sense. Theories need that evidence. Okay, so Big Bang happens, universe expands, cools, fills with hydrogen and helium atoms. But it wasn't just a smooth gas cloud forever, right? How did we get structures like galaxies and stars?
Great question. The key is that the early universe wasn't perfectly smooth. There were tiny, tiny variations in density from place to place.
Like minuscule ripples.
Exactly. Seemingly insignificant, but over cosmic time, they made all the difference. Because slightly denser regions had slightly stronger gravity.
Oh, gravity again. pulling things together.
Precisely. Over millions and billions of years, gravity pulled more and more matter, mostly that hydrogen gas, towards those slightly denser areas. They grew.
Snowball effect.
Kind of like that, yeah. These huge clumps of gas formed, and those became the seeds of galaxies.
Okay, so define a galaxy for us again. It's more than just stars, right?
Oh, yeah. A galaxy is a massive system. Billions, sometimes trillions, of stars, plus gas, dust, and this mysterious stuff called dark matter, all held together by gravity.
They're huge.
Immense. And the distances between them are even more mind-boggling. We measure these distances in light years. Galaxies themselves can be, say, 80,000 to 150,000 light years across.
Light years. Let's pause on that. Crucial for students, right? It's distance, not time.
Absolutely correct. 1 light year is simply the distance light travels in 1 year.
And light is fast.
Incredibly fast, about 300,000 kilometers per second. So a light year is, well, it's about 9.5 trillion kilometers. It's just a more manageable unit for these enormous cosmic scales.
Trillions of kilometers. Can you give us a slightly smaller example? Make it relatable?
Sure. Think about the sun and Earth. The distance is about 150 million kilometers.
Okay.
Light takes about 8.3 minutes to travel that distance, so we sometimes say the sun is 8.3 light minutes away.
Oh, okay. That helps put the light year scale into perspective. It's vast.
It really is.
Okay, so back to galaxies forming from these giant gas clouds. How did individual stars, like our sun, actually switch on inside these galaxies?
So within these huge nebulae, these galaxy-scale gas clouds, gravity kept working its magic. Pockets of denser gas inside the nebula started to collapse under their own gravity.
Contracting.
Right. And as they contracted, they got denser and hotter, especially at the very center, the core.
Pressure building up.
Exactly. Eventually, the temperature and pressure in the core got so intense, maybe millions of degrees, that nuclear fusion could start.
Fusion. Like in a hydrogen bomb.
Sort of, but controlled and sustained. Hydrogen atoms fuse together to form helium, releasing a huge amount of energy, light, and heat. That's what makes a star shine.
A star is born. A giant, stable fusion reaction.
Yeah.
And when did this start happening?
The first stars are thought to have begun forming maybe 5 or 6 billion years after the Big Bang, once things had cooled and clumped enough.
Okay, so Big Bang, then galaxies start forming, then stars ignite within those galaxies. Now, planets. How do they fit into this stellar birth story?
Planets seem to be a pretty common byproduct of star formation. Remember that collapsing gas cloud that forms the star?
Yeah.
Not all of the material falls right into the star. There's usually leftover gas and dust spinning around the new star in a flat disk, kind of like the solar nebula we talked about earlier for our own system.
Leftovers. So planets are made from the star's leftovers.
Pretty much, yeah. Within that rotating disk, the same processes happen again, just on a smaller scale. Gas starts to condense, tiny dust particles stick together, cohesion.
Sticking together again.
Yep. They form slightly larger clumps than larger ones, growing into those planetesimals we mentioned. Dust bunnies, to pebbles, to rocks, to boulders.
Planetesimals, the building blocks. What happens to them?
Then comes the slightly more chaotic phase. These planetesimals, maybe kilometers across, start colliding.
Smashing into each other.
Yeah. But because they have gravity now, they often accrete stick together rather than just breaking apart, so you get fewer, larger bodies forming over time. These are protoplanets.
Protoplanets. Almost planets.
Exactly. And these protoplanets continue sweeping up smaller planetesimals and dust through more collisions and gravitational pulls, eventually clearing out their orbits and becoming the stable planets we see.
So it's this messy process of accretion and collision, building up from tiny dust grains to whole worlds. Okay, let's zoom right into our home, Earth. You described the early Earth as barren, rocky, hot. That was pretty grim.
It certainly wasn't the blue marble we know today. When Earth first formed, about 4.6 billion years ago, from all that accretion in the solar nebula. Yeah, it was a hot, molten rocky ball. Largely, yeah, from the heat of formation and radioactive decay. And it probably had a very thin atmosphere of hydrogen and helium left over from the nebula, but that early atmosphere didn't last long. The young sun was much more active, sending out strong solar winds.
Which just blew it away.
Pretty much stripped it right off. Happened to all the inner rocky planets.
Wow. Harsh neighborhood, the early solar system. So how did we get from that barren, hot rock to, well, this? What changed?
A whole lot changed over 4.6 billion years. Key things were the planet cooling and developing its internal layered structure, then volcanic activity creating a new atmosphere and eventually the oceans,
Mm.
and finally, of course, life emerging and changing things even more.
Okay, let's take those one by one. The
Go on.
layers, like an onion, right?
Right.
Crust, mantle, core. How did that structure form?
Right. So remember the early Earth was mostly molten?
Yeah, hot and gooey?
Because it was fluid, materials could move around, and gravity pulled the heavier stuff downwards. It's a process called differentiation.
Differentiation,
Wrong.
separating things out.
Exactly, based on density. Heavy elements, mostly iron and nickel, sank towards the center. They formed the Earth's dense core.
Makes sense. Heavy stuff sinks.
While lighter materials, things rich in silicon, oxygen, aluminum, kind of floated upwards, like slag in a furnace almost.
Floated?
Effectively, yeah. As the Earth started to cool from the outside in, this lighter material solidified to form the outer layers, the mantle, and eventually the crust, the rocky skin we live on.
So gravity sorting everything by weight in a molten planet.
Mm.
But I remember reading something about the moon, that its formation affected this.
Oh, absolutely. The leader theory for the moon's origin involves a massive impact.
An impact.
Yeah, early in Earth's history, maybe within the first 100 million years or so, a huge object, maybe Mars-sized, is thought to have slammed into the young Earth.
Oh.
A cataclysmic collision. It threw a vast amount of debris into orbit, which eventually clumped together to form the moon. But the impact itself added a tremendous amount of heat to Earth.
So it remelted things, helped the differentiation.
Likely remelted much of the outer layers, yeah. It would have given that differentiation process another big stir, ensuring the heavy stuff really got to the core and the lighter stuff ended up closer to the surface before things finally started to cool and solidify properly.
A giant impact shaping our planet's structure and giving us our moon. Incredible. Yeah. Okay, so differentiation gives us layers. Crust, mantle, outer core, inner core, getting denser as you go deeper. Now, what about the air and water? How did we get from that stripped-off early atmosphere to oceans and the air we breathe?
Right, the atmosphere and hydrosphere, the water. So that primary hydrogen-helium atmosphere was gone. The second atmosphere came from inside the Earth itself.
From inside, how?
Through a process called degassing. Remember all that heat and volcanic activity on the early Earth?
Yeah, lots of volcanoes.
Well, those volcanoes released enormous amounts of gases trapped within the Earth's mantle, things like water vapor, lots of it, plus carbon dioxide, nitrogen, methane, ammonia.
So volcanic burps created the atmosphere.
Essentially, yes. That was the source of Earth's early secondary atmosphere. But notice what's missing, or present, only in tiny amounts.
Oxygen.
Right? Exactly. Very little free oxygen in that early volcanic atmosphere. It was mostly water vapor, CO2, nitrogen. Not breathable air for us.
Okay, so full of steam and other gases.
Yeah.
How did that turn into oceans and an oxygen-rich atmosphere?
First, the oceans. As the planet slowly cooled, all that water vapor in the atmosphere started to condense.
Like steam turning back into water.
Yep. And it started to rain. And rain. And rain, probably for millions of years.
Wow, a global downpour lasting millions of years.
That's the picture. This torrential rain filled up the low-lying basins on the Earth's surface, forming the first oceans. This probably happened relatively early, maybe within the first 500 million years. So our oceans are ancient, maybe 4 billion years old.
4 billion-year-old oceans.
Yeah.
Amazing. Okay, oceans formed from condensed volcanic steam, but the oxygen, where did that come from?
Ah, now that's where life changes everything. This is the third stage of atmospheric evolution. Yep. Early life forms, probably starting in those oceans, eventually evolved a new trick: photosynthesis.
Using sunlight for energy.
Right. They took in sunlight, water, and the carbon dioxide that was abundant in the atmosphere, and they produced energy. But as a waste product.
Oxygen.
Oxygen. This probably started around, say, 3 to 2.5 billion years ago. At first, the oxygen reacted with stuff in the oceans, like dissolved iron-forming banded iron formations you see in rocks.
So it was being used up initially.
Yeah, the oceans acted like a sink. But eventually, life produced so much oxygen that it saturated the oceans, and then it started building up in the atmosphere.
Filling the air.
Exactly. Around 2 billion years ago, atmospheric oxygen levels really started to rise significantly, paving the way for the kind of life we have today.
So life didn't just adapt to Earth, it fundamentally changed it, especially the atmosphere. Profound. Okay, final huge question then. When did life itself actually get started? You said the early Earth was pretty hostile.
It really was. Intense radiation, no oxygen shield, volcanic chaos. Not comfy. But the current scientific thinking is that life arose from chemistry.
Chemistry.
Yeah, a process where simple inorganic molecules reacted, maybe near volcanic vents or in shallow pools, forming more complex organic molecules, things like amino acids, nucleotides.
The building blocks of life.
Exactly. And eventually, somehow, some of these molecules developed the ability to replicate themselves, to make copies. That's the key threshold for life.
Self-replication. The spark. Is there evidence for when this happened?
The fossil record gives us clues. There are microscopic fossils, structures that look very much like simple bacteria or blue-green algae, found in rocks that are incredibly old.
How old?
Some of the oldest convincing evidence points to life existing perhaps as far back as 3.8 billion years ago.
3.8 billion. So life got started relatively early in Earth's history, despite the conditions.
It seems so. Even in that challenging environment, life found a way. And as we discussed, it then spent the next billion years or so evolving things like photosynthesis.
Which then saturated the oceans with oxygen.
And then flooded the atmosphere starting around 2 billion years ago, setting the stage for more complex life, like us, much later on.
What an absolutely epic story. From like a infinitesimally small point through cosmic expansion, star birth, planet formation, differentiation, degassing, and then life itself emerging and reshaping the planet.
It's an incredible chain of events, isn't it? Stretching over billions of years, each step built on the last. The Big Bang making the elements, gravity pulling them together, geology setting the stage, and biology transforming it.
Yeah. For anyone studying this, just hitting those key points is crucial, right? The Big Bang, the evidence like expansion, and the CMB.
Definitely. Then the stages of star and planet formation, nebulae, accretion, planetesimals.
Earth differentiation, creating the layers, the degassing for the atmosphere and oceans.
And don't forget the 3 stages of atmospheric evolution, including life's role with oxygen, plus the timeline for life's origin and photosynthesis.
Getting those core concepts in the sequence down really gives you that solid foundation.
Absolutely. It helps understand not just Earth science, but our whole place in the universe.
Totally. And maybe a final thought to leave everyone with. After hearing this immense story, this like improbable journey from a singularity to us, what comes next for Earth? What's the next chapter? And, what's our role in it?
That's the big question, isn't it? A humbling perspective.
Definitely something to think about. Keep exploring this stuff.
Yeah.
Physical geography, cosmology. It's fascinating. Thanks for joining us on this deep dive.